welcome to another session of solid state. In this session we will be talking about different close packing structure and the arrangement of different atoms, plus we will be focusing also on the void, that is the tetrahedral and octahedral voids which are formed in the process. So let's start. Now, if you focus in close packed structures, the close packing in one dimension can be done in this manner. That is, these are the atoms. If you arrange them in one line, that is only in one dimension, you see that they are in this manner. So if you choose any atom, it is actually having two neighbors. So the coordination number is 2, because what's the definition of coordination number? That is the number of nearest neighbor of a particle. So if you choose any one particle that is in the middle, this one, let's say it is having one neighbor, this one, and another neighbor, this one. So this is one dimensional close packing. Now let's go on close packing in two dimension. So if you choose a structure A, basically copy this, paste it over here, paste it over here, paste it over here, and you see that this is your A pattern of close packing in two dimension. Now if you choose any randomly an atom or a particle, you see that this particle is attached with 1, 2, 3 and 4 other particles. So basically the coordination number is 4. So two-dimensional coordination number is 4 in square close packing in two dimension. Similarly, if you try to place a layer A with little bit shift, so since there is a little bit shift, we call this as a layer B. So layer B is actually like this. So AB pattern is this one, that is hexagonal close packing. Now why the hexagonal close packing? Because if you choose any randomly constituent particle or an atom, you see that it is connected with 1, 2, 3, 4, 5 and 6 atom. That's why the coordination number of hexagonal close packing in two dimension is 6. Okay, so this was about two dimension. Let's go to three-dimensional close packing. Now focus on this, that is your A square close packing. If you place another layer on top of it, don't you think you will get this type of structure? That is, this is your layer A. Okay, another layer same, which is this one, A layer. So this is also a simple cubic lattice which is formed by A arrangement. Each layer is your A arrangement. So this one is actually having a coordination number of 6. If you choose any one atom, there will be 4 on the same plane, that is one here, here and one in the front which is not there, and one on the top and another on the bottom. So this is a typical structure of NaCl. Now let's go to next is three-dimensional close packing for from two-dimensional hexagonal close packing layer. Now if you do this, we create tetrahedral and octahedral void. What is a void? Void is actually the empty space which is present in between the constituent particles or atom. Let's go in deeper detail. If you see here, these are my three constituent particles, or let me call them atoms. So these are my three atoms, and if I place my fourth atom on the top like this, so there is a tetrahedral void which is being created here, because if you join the centers of all these atoms, you get a tetrahedron structure. So this is your tetrahedral void. So this is by placing second layer over the first layer. Next is another way is actually if you place little bit aside. So if you place this is your lower layer, that is represented in blue, and the red one is the top layer, which is this one. So if you see, this here is giving you an octahedral structure. So this void or the empty space is actually called as your octahedral void which is present. Okay, now let's see the number of tetrahedral and octahedral voids which are formed. So let the number of close packed spheres be n. So these spheres are known as close packed spheres. If the number is n, the number of octahedral voids generated is n. and the number of tetrahedral voids which are generated are double the number. Please remember that if the number of closed packed spheres are n, so number of octahedral voids will be equal to the number of closed packed spheres, and then if the number of tetrahedral voids will be double of it. Okay, so this will help you for solving numericals. Let's go ahead. Now, covering the tetrahedral void, so the pattern which is often written as ABAB pattern, this structure is called hexagonal close packing, that is HCP structure. So just to show you, HCP structure is this. Basically you have this A layer, okay, this is your B layer. So here you are putting this atom and this atom. So don't you think that you are creating a tetrahedral void, okay, on top of this, and you are covering that tetrahedral void. So here the pattern is actually obtained in ABAB form, okay, that is covering tetrahedral voids. Whereas if you cover the octahedral voids, how the octahedral voids are covered, if you focus on this figure, let's say this one here, from B to C there is an octahedral void, okay, so this and this creates your octahedral void. If you cover this octahedral void from below and from top, you get cubic close packing, that is CCP structure, or it is also face centered cubic structure. So these some of the examples of HCP structure is magnesium and zinc, and some example of this is such as copper and silver, that is of FCC or CCP structure. Now both of the close packing are highly efficient. Basically in the next session we will see the packing efficiency calculation. So both the close packing, that is HCP, FCC and CCP, have a packing efficiency of 74% and the coordination number is 12 in either of the two structures. So please remember that in this case, in 3 dimension, FCC, CCP or HCP, we have 74% of packing efficiency and the coordination number is 12. Okay. So I think this diagram is clear. This is just ABAB pattern. If you use ABAB pattern, you get hexagonal close packing. If you put ABC pattern, that is your cubic close packing. So this is another way of representing ABAB. This is your ABC, and it will go on. So as already told you, like let the number of, like in HCP or CCP structure, there are 2 types of void generated, that is tetrahedral and octahedral void. So if the number of closed packed spheres is n, so number of octahedral void will be n and number of tetrahedral voids will be double of it, that is 2n. So while the number of octahedral void present in the lattice is equal to the number of closed packed particles, the number of tetrahedral void generated is twice this number, that is already explained. If it is n, this will be 2n. An ionic solid, now this is important, the bigger ions, that is usually an anion, we all know that the size of anion gets bigger. Reason is they take in 1 electron and that's why the effective nuclear charge decreases, so the size increases, form the close packed structure. So these anions, they make the main constituent particles, that is the main lattice, and the smaller ions, that are usually the cations, occupy the void spaces. If the cation is small enough, then tetrahedral voids are occupied. If it is bigger, then octahedral voids are occupied. So also please note that not all octahedral or tetrahedral voids are occupied. So thank you for this session. Okay, see you all in the next session. I hope you enjoyed it. Thank you.